Now, I believe our next presenter, and we are a little bit ahead of time, is Mike Gamble. Sir, would you be willing to go a little bit early?
That's no problem.
Okay.
First thing I'd like to comment on was what Frank was just saying. He's right on the money. No comment there. The other one is Glenn. This paper that I'm presenting was originally presented at Glen's Space Propulsion and Energy Science International Forum when I was still employed at the Boeing Company. That's the origin of this. One of my comments is that there's a lot of gravity presentations out there that infer a connection between electromagnetics, and this one I kind of show the numbers on that connection. Let's see, I got to get the screen share running here. That's the first one. Let's see, I got to get a screen up first. I guess that's, how do I do that? Okay. Screen share. Gravity. Oh, here we go. There we go. Okay, can you see that?
Yeah, looks great. I think you're all set.
Okay, then we're ready to rock and roll. If we're sharing anyway, what I just said here, this is a continuation of my study of gravity. The first part was on what it is and what the equations of it was. And this one takes the end result equation from the first part and converts it over to electromagnetics. We got a lot of Maxwell's equations in there to keep everybody happy, I guess. Let me get this thing going over here to slideshow. From the beginning. There we go. Okay. And then, of course, the next page is that Boeing allows this to come out into public domain. I noticed there was a few comments about Boeing there doing hidden work, and I can't comment on it, but I will say that they do things like that. Anyway, this presentation is allowed to be out in public domain. As a matter of fact, it's been out there about 10 years. So this is nothing new. However, it's probably new to a lot of people. This one is a little out of date. I'm now retired. When this was originally presented, I was still employed at Boeing. At 2009 is when it was presented, and it's, I would say, still relevant. Nobody has told me that it doesn't work. Basically, it's field theory. And okay, the tutorial is, this is kind of an outline of what it is. I started with electromagnetic field generation, and then as that ties into Schumann resonance, which is one of the key points of working here on planet Earth. And then the second tutorial is on AC and DC dipoles and electromagnetic equations. And the third one is on the traveling and standing waves. And then the main section is on the EM field generation with respect to gravity. I happen to use cylindrical coordinates instead of spherical, which is what most EM work is done in. I'm not a fan of spherical coordinates. And then I conclude with a couple of proposed space drives based on that data. Starting with Schumann's resonance, back in part one there, I just mentioned it. This one I do a more detailed analysis because this is part of the system that we have to live in. Or if you go to the textbooks and look up open-ended cavity resonators, you can get this diagram here along with the transfer function. This is a spherical or three-dimensional cavity. It supports all harmonics, fundamental, second, third, fourth, on up, because it's open-ended. Basically, the cavity is a dielectric media located between two electrically conductive surfaces. You got the inner and the outer. And the equation uses Rm, which is the mean radius. And then you have the electric permeability, of course, and then magnetic permeability and permittivity to deal with, which is your dielectric stuff. What I did was take that and put that in perspective here, how the Earth is. The Earth's resonant cavity, the inner radius is the surface of the planet. It's conductive. All your electrical systems grids are all grounded to it. The outer radius is about the middle of the ionosphere because that's conductive. That's about 100 miles up. And so that puts the mean radius at about 50 miles, which is the outer edge of the atmosphere. And then you have magnetic permeability of non-ferrous materials is mu of 1. And of course, the dielectric constant of air is 1. So you have your numbers. So the next step is we go and we crunch those numbers in the equation, plug it all in for the Earth, and you come up with a frequency of 10.45 hertz. However, what the problem is the Earth is not a perfect resonator. The actual number measured for Schumann's resonance is 7.83 hertz. So taking a look at why it doesn't work, first you got the ionosphere, which is only a partial conductor, and it's influenced by solar flares, lightning, day and night cycles, and a whole bunch of other stuff. And the inner conductor of the Earth's surface doesn't have a constant radius. There's mountains and valleys. The smoothest part is the oceans. And the dielectric media, air, it's not exactly homogeneous. There's dirt, dust, pollen, water, and of course, electrical short circuits, lightning being the worst one. So if you take the equation and you tweak it, the terms, the gain and offset terms, back them down a little bit from 1 to 0.69 or 689 and 0.433, and rerun the numbers, it will come out exactly on the numbers as the Schumann's resonance is given. And what that shows is that it's a 30% reduction in the efficiency of the system. So therefore, the Earth only operates at 70% efficiency on the Schumann resonant cavity. This one takes the details a little bit more. Because it's a tuned circuit, you have a Q point and a narrow bandwidth for your different harmonics. Now, the fundamental is 7.83, second is 1407, third is 2025, and the fourth is 2641. Now, the driving frequencies from the gravity equation are 7.07, 14.14, 21.21, and 28.28. So if comparing the resonant frequencies to the driving frequencies, you see that the driving frequency for the fundamental is very close. So you're going to get about a 90% gain on that one. The second harmonic's even closer, and I would say you would get 100%. Now, when you get down to the third and fourth harmonics, they start losing it. So you're 60% on the third and 30% on the fourth. And then I graph that down below as far as the calculated versus the data. And the third harmonic is even lower than what's calculated there, as you can see from the chart. Now, superimposing the Schumann resonance on the planet, see where these are standing waves. The fundamental is down in the mantle, And then all the rest of the higher harmonics, second, third, fourth, and fifth, are all down in the core. And like I said, these are all standing waves. And that's what determines the magnetic parts of the Earth and provides friction, heat, movement as far as the core materials down there, which is what keeps this planet going. Next, we'll move on to DC and AC electromagnetic dipoles and all the equations that drive those. It gets a little bit messy here. Starting with the easy one, DC electric dipole. Textbook equation there is two equal and opposite electric charges separated by a distance. Using cylindrical coordinates, I place the dipole on the z-axis equally spaced around the origin. And then you have the field from the plus and minus terminals charges. And then, of course, at close range, the two electric potentials interact, causing a difference. In mathematical terms, that's a gradient. And we'll get into the details of that. As the system is DC, there's no magnetic field generated. And flipping the page here, this is where it starts getting nasty with the equations. So we start with the electric field potential, which is V, and you have all the equations for that. And then you take the gradient of that, you get the electric field, and that gets a little more messy. And then the B field, there isn't any because it's 0 on the frequency. And so the electric field potential rolls off. It's measured in volts. It rolls off 1 over the distance, or 1 over R, however you like it. And the second field, the electric field, is defined as the negative gradient, which rolls off volts per meter as 1 over R squared. And like I said, there is no magnetic field at the DC level. So then we go over to the magnetic field. This is the DC textbook equation for the magnetic field. And it's two opposite poles separated by a distance d. Same thing, cylindrical coordinates centered about the origin on the on the z-axis. And close range, you have the gradient, which is now delta operator because there's a spin involved. And the system is steady state, like the electric, so there's no electric field. However, there is a little bit of difference between the magnetic field and the electric field, because the magnetic field has spin, even though it's a DC or steady state type field. And that generates a tuned length, which neither one of those two is talked about in textbooks very much. So a bar magnet is actually a half wave device. And then we'll get over here to the nasties on the equations. It starts off with the magnetic potential, which is in the theta direction. And it's measured in Webers, and it rolls off at 1 over R. And then you get down to the field, which is the, in this case, it's the curl rather than the gradient, del A, to get B field. And that breaks out into two fields, the radial field, which is BR, and the Z field, which is up and down. And that's measured in Webers per meter squared, and that rolls off at 1 over R squared. And because it's steady state, the E field, which is the curl of the magnetic, is 0. Now to convert from DC to AC, there are other ways. I happen to use Euler's formula, which is all the sines and cosine terms are converted to exponentials, which are a lot easier to integrate and differentiate. Euler's formula up there, you can take the sine and the cosine and get an exponential. Now, the second modification is convert over to what's called AC phasor notation. So electromagnetic fields use a simplified term where they only use the displacement part, the 2 pi radius over the wavelength. The omega t term is dropped because all AC waves are assumed to oscillate. So that's kind of a superfluous part. And then the third part is you multiply the DC equations by the AC phasors, and that completes the process. However, when you start differentiating and integrating, it gets pretty messy to deal with the AC side. So starting with the electric field, AC, going back to the textbooks, you still have the same charges separated by the distance, which D now becomes a half wavelength for the AC electric side, where it didn't matter on the DC side. And because it's now oscillating, you have a B field that is generated in the axial direction or circular, however you want to look at it. And then we go to the nasty page here with all the equations. As you can see, they get a lot worse because it's AC. Starting with the electric potential, you now have the two terms plus the exponential, which is your sinusoids. And the potential still rolls off at 1 over R. And the E field rolls off at 1 over R squared. However, it's now modulated because you have frequency in there. And you get 2 E fields, one in the R direction and one in the Z direction. And they get even worse. And then you get down to the magnetic field, which is the curl of the E. You now have a back and forth oscillation in Webers per meter squared. Now we'll go over to the magnetic side. This is the AC magnetic term, starting off with the magnetic potential, which again is at half wavelength. And it's centered about the origin on the cylindrical coordinates. And the big difference on the AC now is it also generates a E field, which is circular in the theta direction, which you didn't have last time because it was DC. And going over the equations, they just get worse. I don't even like going through the numbers, just plug them into the computer and let it crunch it. When I did this programming, MATLAB choked many times when I was drawing the field plots because the numbers would back up in the on the system there. But anyway, you have the magnetic potential, and that still rolls off at the 1 over R, and the Webers per meter second, which is your B field, is now in the BR and BZ directions. And they get nastier as you do more integration there. And then you get down to the volts, which comes in volts per meter now, in the theta direction or radial. And the problem is all these equations are only for one frequency. When you start working with harmonics, you have to duplicate that, all the equations 3 times for all the harmonics, and it gets pretty messy. Like I said, I just type them in and I try not to think about them. I don't like the math, but it's required to do the job. Next one, we'll talk about standing and traveling waves. Because I'm trying to give a few little basic tutorials. So when we dig into the equations for doing the math for the planet, it won't be too cold turkey. The E field, I use color coordination. I should have said that up front here. I use green for the electric, and I use red for the magnetic, and then for the acceleration field, I use blue. And the next charts, I take each one by phasing. I start with 0 phase, and we just do a few textbook type work here where you have the electric field on one axis, and then at 90 degrees or orthogonal, you have the magnetic field. And the phasing here is 0 phase. And when you do the vector product, E cross B, that generates a force. And so you have the E field. The B field is positive maximum starting here, which makes the E field a negative maximum. When you do the cross product, you get a force field generated, which is the blue arrows, and they point to the right. I also have a little dotted sinusoid up on top, which represents the arrows. However, the direction would be in the other axis, but I decided to put it up that way so you could see it better. What there is a sinusoid at twice the frequency of the fundamental of the E and B field that generates the force field. And because the sine wave is off-centered, it generates a DC force, which causes the wave to move to the right. It gets pushed. That's also not part of what you normally get in the textbook. There's actually a force being generated in the field. And now we do the same thing, only now the phasing between the E field and the B field is at 90 degrees. So when the B field is a positive maximum, the E field is 0. So when you do the vector cross product, the field represented in the blue arrows, as you can see, every other cycle points to the left and to the right, so they nil out and cancel. So you have a standing wave because there's nothing pushing it. It just sits there and bounces up and down. If you look at the little dotted one, it's centered right on 0. It goes positive, goes negative, goes positive, goes negative. You take the average, it's 0. So the wave isn't going to move any place. And then we go to 180 degrees. This one is when the B field is at positive maximum, the E field is a positive maximum, and you do the E cross B, and you get a negative wave pushing to the right, or to the left this time, so it goes the opposite direction. You can see all the force arrows are all pointing to the left, and then you look at the little dotted sinusoid. It is now pushed negative, so it generates a negative force. And here again, the force pulses are twice the frequency of the fundamental, what generates it. And then the last one, we go here to 270 degrees, which is another standing wave. When the B field is at maximum, the E field is at 0. And you do the E cross B, and you get nothing for the generated force. It's a sinusoid that just sits right around 0. And you look at the arrows, and they again cancel out. The blue arrows for each cycle are equivalent and opposite directions, so there's no force pushing this wave anyplace. And then we do a little tally here at the end for a summary, that at 0 degrees, the force field of the wave is pushing it to the right. You go to 90 and it stands still. You go to 180 and it shifts gears and goes backwards the other way to the left. And then again at 270, you hit a negative standing wave. And so you get standing waves for 90 and 270, and you get traveling waves for 0 and 180. The key point that I want to make is that the resultant field, the force field, is double the frequency. There's frequency multiplication involved, and this gives a little clue to the connection to the acceleration force of gravity, which is pretty much the same thing, only instead of the E and B fields being linear, they're sort of circular, so the field is getting pushed a circular direction rather than linear like it would be for transmitted EM or EM wave. Okay, now we're going to back up and bring in the data for the equations from part 1, which was the end of the part 1 result, was a mathematical equation for the acceleration of gravity. However, now we're going to be dealing with electromagnetic fields and imaginary numbers and calculus and all that good stuff, which makes it a mess. Now, when this was originally presented, I had a few typos that were pointed out to me from part 1, and those were all corrected in the 10 years it's been out. So we don't have to talk about the errata list. This is the one where it comes in from part 1. The black dotted line was the equation that was generated from part 1, showing all the different parts. Now this is at the equator radially outward. The first one there, you have the surface value, which is what they quote in the textbooks. It's 32 feet per second. And then this is in the metric term, which is 9.807 is meters per second squared. And then you get out there, the little dot up there represents the center of the inner radiation belt. And then you go out to the outer radiation belt, which is at a half wavelength. The inner one's at a quarter wave, the outer one's a half wave, and geosync orbit sits out there at full wave. And then you go out another full wave and you hit the outer edge of the magnetosphere. Now, what I did was on that black dotted one, which is 1/r roll off for the terms, I put on the blue, which is, the blue is 1/r squared, and the red is 1/r cubed. What I was trying to see was what effect the different roll-offs had on the field. Now, as you can see, it's mainly under a half a wavelength. They increase the field strength in the core of the planet, and they also increase the strength of the inner and outer belt. But after that, they pretty much don't do anything. It all tapers off because you get to the far field pattern. So there's not much difference in the fields of that distance. Now, next picture is the same thing, only this is in the z-axis, which is up and down. And so you see there's a big difference in the core values, and in the when it comes up to the surface, the roll off for the inner and outer belts. And those spikes probably generate your aurora borealis, or your northern lights, or if you're on Australia, it'd be southern lights. It's a residual from the field pattern. Okay, next one is we need a force equation to do our work. So this one I started with the Poynting vector, which is E cross B, which gives power density, watts per meter squared. And because force, or the force vectors and that power, energy, and all that are all fairly close. Basically, it's just a change of constants. So first I remove the magnetic permeability constant, which reduces the equation from watts per meter squared to Newton ohms per meter squared. And then the free space resistance is equal to the permeability divided by the permittivity. And you put that substitution in there. And then the last one, you have to flip it over because it's the reciprocal of the free space. And you wind up with force is equal to the length or the radius squared divided by the square root of E0 over mu0 times E cross B, and the end result comes out in newtons. That's one way of generating it. Another way of generating it is the left-hand motor rule, which is actually the Lorentz force equation, which says force is equal to the length of the conductor times the current vector product of the B field. And you can modify this equation the same way by I, which is the current, is also equal to the V over R, which is Ohm's law. And you substitute that in there. So V becomes E when it goes to a field, and R becomes the resistance of free space, mu and E or epsilon square root. So you plug in those modifications and you get the same thing, L squared, which is the distance or length, depending on what direction you're going, square root of epsilon over mu, E cross B in newtons. So there's two ways you can drive the force equation from E cross B. Taking that a little bit further here to see how messy it is, the vector equation has four terms. First thing you need to point out is they're all orthogonal. That's why I use the color coding. The force vector, and then the E vector is in the theta direction. So when you start multiplying all this out, you get individual B field vectors, and you also get imaginary numbers to deal with in there. However, there are two basic possibilities. Either the E field is in the theta direction or the B field is in the theta direction, and the other one is in the Z direction. Well, looking how the Boy Scout compass works, I would say that the B field is the one that goes in the Z axis. That makes the E field go in the theta direction. So for the first cut, that's the way we did, which is actually the second one there. Now we go back and we're dealing with beat frequencies or wave mixing. Heterodyne is the technical word. So you take a B field, which has three terms, a constant term, and two, the fundamental and the harmonic as being cosine. And you take an E field, which is a second harmonic, and it's sine, so there's a 90 degrees phase shift between the B field and the E field because sine and cosine are at 90. When you do the cross product, you come out with four terms. Now, what you get on beat frequencies is you get the original two frequencies, which would be the E and the B, and then you get the sums and differences. And I highlighted those, so we got four terms, which the difference, the double, the sum, and the two theta. For your beat frequencies. Now that's what's going to wind up as being the force vector. Now the constants, F1 is equal to E2 times half of B1. F2 on that constant is equal to E2 times B0. And F3, the constant there is E2 times half of B1. And on the constant for the fourth harmonic, it's E2 times B2. Now you look, they're all sines, so the phasing is the same there, and they're all in the negative direction. So now we go back to the part one chart there. The black dotted line is the original data from chart one, or from the first part. The green is the second harmonic electrical field superimposed on it. The red is the fundamental B frequency superimposed on it, and the blue is the E cross B, which is the force vector. Now you take a look at the force vector versus the empirical equation from part one, and you see it lines up almost perfectly. It also corrects a small error on the inner belt. As you see, the center dot is not at the 0 point from the first equation. However, this force field equation pulls it back to where it should be, centered at the 0 point. And it also pulls the overshoot on the surface there back to the surface marking right on the money. Going down and looking at the equations there, the B field, these are the values. They have pretty big numbers because like to the 15th power, the 10th power, the 13th power, that's all at the center. But as they go the 39,000 or 3,900 miles from the center to the surface, by the time you measure them up on the surface, the B field is down to microwebers and the E field's down to millivolts. But the main point here is the tracking of the force field is almost exact. Now I switch over and I do a FFT on the frequency from the gravity picture of part 1, 703 hertz, 1406, 2109, and 2813. And then the relative amplitudes, you got 1 for the fundamental, 1.5 for the second harmonic, 1.2 for the third, and 1.1 for the fourth. And this is the acceleration from the part 1. Now, this chart looks almost identical, which is the relative power and from the force field that we generated with the E cross B. It looks almost identical. The frequency numbers are just a hair difference because this is 707, 14.1. This is your driving frequencies. Amplitudes are almost identical. It's 1 for the fundamental, 1.5 for the second harmonic, and it's 1 for the third and 1.1 for the fourth. They're too close not to be related. Next one, we go and take a look at the individual frequencies. Okay, this is the B field. All the nasty mathematics there, the fundamental DC term, and then the first harmonic and the second harmonic. So the total in the radial direction is you take all 3 of those and plug them into MATLAB, and it gets pretty bad. The Z field is about the same, and to get all those numbers crunched, the higher terms, the imaginary terms, which are called the near field terms, they roll off at the 3rd power and the 5th power. So by the time you get out to half a wavelength, they're down to nothing, which is what the first chart showed. So you're left with the real terms, which are your far field terms. Same goes for your E field. This is the complete equation. Now this runs at the second harmonic of the B field. So this would be starting at 14 hertz. And there's no constant or DC term, and neither the first harmonic. However, there is a 3rd power imaginary term for the near field pattern. And this one is pretty much the summation of everything there. You take the B field and the E field. The B field has a constant of double, and then its fundamental is 1, second harmonic is 1, and over your roll-off term in Webers per meter squared. And then your sign on the second harmonic for the E field in volts per meter. You do the vector cross product, you get the force field, which is sine with a constant of 1, second theta or second harmonic 1.5, 1 for the third, and 1.1 for the fourth. And then you take a look at the acceleration vector, and The only difference is on the third order term, one is 1.0 and the other is 1.2. Other than that, they're identical. And Mr. Newton, according to his law, F equals ma, that also works for fields. And so you take the acceleration field, the A, which is black, and the F, which is in blue, and you look at the constants there. One is e to the 10th and the other is e to the 13th. Well, the difference between those two is when you convert Newtons, Newton comes up as being kilogram meter second squared. So the second one is in kilometers. So you have to multiply by 10 to the 3 to do the conversion. When you reduce the terms, guess what? M comes up as kilograms. So it all matches perfectly. And the waves, the force and the acceleration are just too close not to be generated from the same source. Now we get to some of the prettier pictures that MATLAB generates, starting with, this is the B field. The black circle in the middle is planet Earth. The little bar, vertical bar, is the dipole in the planet. The first dot is the inner belt, center of the inner belt. The second dot or star there is the center of the outer belt. G stands for the geosynchronous orbit, and M is for the magnetosphere. And you can see the AC terms there. You got the spinning vectors and you got your potentials. So they're grouped together. And if you look at the B field at the center of the center of the outer belt, it's a negative, and it's positives on both where the node is for the geosync and for the magnetosphere. We'll kind of zoom in. I got a closer view. That was a 500,000 kilometer view. This is a 50,000. This only goes out to geosync. And so you can see that the here you have the inner belt, big positive there, and the outer belt, you have a big positive there. And then you have all the waves lining up here due to the frequencies. This is running with all 4 harmonics. Primary one, of course, is the 7 hertz. And then you got your potential lines. This is your DC magnetic field. And then you get your AC term around there. And you get a big, strong field up and down, which is your DC term, which is what your compasses track. And then we'll go over here and we'll superimpose the E field on this. Now this is going back to the 500 kilometer view, which goes out to the magnetosphere. So you see the E field lines up as shells, alternating shells back and forth. And then you have the center point, the node across the axis. Next one, we'll zoom in here. It's a lot easier to see. So now you have the B fields, okay, where the 2 shells for the outer belt and the inner belt are sandwiched in between the nodes. You see the green line goes right through the centers. The nodes are the E field nodes are where the belts go through. Same out here when you get to geosync, you got on the E field, goes right through the nodes. And then the E fields, like I said, they're in shells and they spin back and forth where the magnetic field goes up and down. And then the next chart, we go back out to the 50,000 or 500,000 kilometer and we throw in the force field or acceleration field, whatever you want to call it. And you can see the area, close-up area where it is the strongest. When you get out here to the magnetosphere, the little blue dots are just dots. There's very little error, but in here they're quite strong, and right around the planet it's even stronger. And then we'll zoom in for a close-up here, and you can see the individual vectors now. Green is electric, and red is the magnetic, and then the force field. They're all orthogonal as far as the near or the far field. When you get down into the near field, because of the imaginary numbers, there's points where they're not exactly 90 degrees, they're a little bit off. But what you can see is here out at geosync, you got the magnetic field going in the same direction. However, the E field is reversed. It's sitting at a node, so therefore the force vectors are now canceling each other, which makes a physical node right there. And you get a similar thing here, but because the vectors are not at 90 degrees, you get a spinning. One spins one way and the other spins the other way. And the same thing happens to the planet. It works like a big electric motor. The field is a little bit off, so there's a spin generated. And then you got your alternating shells. Now, all these pictures show only 1/2 cycle of the AC. When the B field will reverse from up to down, and the E field will spin the opposite direction, but the force vectors do not change direction because of the cross product. They just pulse in and out from 0 to maximum and back and forth. And so we'll just kind of sum it up here a little bit. At wavelengths less than one wavelength, or at waves less than one wavelength might be a better way to express that. They're not a perfect 90 degrees because the imaginary part, or the near field, which is the standard way of expressing it, causes the imbalance. Now, this is mainly the planet's surface, the inner belt and the outer belt. Once you get past that, it stabilizes. And when you get out to geosync and the edge of the magnetosphere, they're all at 90 degrees. And the magnetic dipole length at quarter wave is 10,606 kilometers. And basically that's down in the mantle area. It's under the crust, so it's inside the planet. And then we talk about the conclusions here. The accelerating force, commonly called gravity, is a resultant force directly from the interaction of E cross B. So not only related to the electric and magnetic fields, it's actually generated from it. And then we're talking about the back and forth movement. The electric field spins back and forth like the agitator in a wash machine. It just oscillates back and forth. And then the B field goes up and down, so it actually turns around. And these gravity pulses are at 14 hertz, which is the second harmonic. So there's 2 pulses per cycle. So at 14 hertz, that's 14 pulses per second of this force field being applied to everything on the planet, which is what keeps you glued to it. And so then the third harmonic and the fourth, all those drive. The fourth mainly controls the generation of the radiation belts, and the second and third harmonic is what contributes most of the waves. This in turn drives the leaky resonant cavity system known as Schumann resonance, which gives us the background pattern on this planet, which sustains life. Now, NASA carries Schumann resonators on board the space shuttle and also the space station because it's when you leave this planet, your body starts degenerating or deteriorating, and this being in close proximity to a Schumann oscillator, if you will, slows that process down. It's part of the Earth system, if you will. Now we get to the fun part. Applications based on the learning, if you will, of the gravity force field generation. I come up with a couple of ideas for some space drives. One I call Tesla drive, and the other I call a warp drive, just for lack of a better name. The first one, reason I use the Tesla term is it's based on his operating principle, which works very similar. Like I said, gravity works gravity and this planet work very similar to an induction motor. It's the same E cross B that Tesla uses on electric motors, and that's where I picked the name for that. Now, the other one is he did the motor work about a century ago, so it's kind of tried and true. The main difference is I just turn the motor on end. Starting with the basics, on an electric motor, you got a magnetic pole, two north and a south, which generates a magnetic field between them. Then you have an armature. Now, I don't show the magnetic field, the core of the case. I also only show one armature pair. There's around the armature, there's many pairs, but for simplicity, I just show one pair immersed in the magnetic field. The vector cross product is a force vector this way and a force vector this way, which makes the armature rotate. Now, you can look at the top view of the same thing. You got your armature here, the shaft, one field pair, and then you magnetic field. Now, this is only one pulse or half a pulse. Now, in the electric motor, the second half of the cycle, the north pole becomes the south and the south pole becomes the north. The E field also turns around. However, the same thing happens. The force vectors just pulse. They do not turn around because of the vector cross product. The next type of motor we'll talk about is a linear induction motor, which is basically you take the rotary motor and you unwind or unwrap the armature and the stator, and you lay them out flat, and it still works by the same principle. Now, I removed the front side of the magnet so you can see the eddy currents. The armature now becomes just a flat plate, and the magnets are now into the page and out of the page, and the eddy currents cycle around. However, all the force vectors point in the same direction, so this armature would pop out the side. Now, this is one half of the AC cycle. Now, the other half, all these magnets would turn around. The E field would cycle the other way, but the force vector would still be out to the right. Next picture shows a top view with both sides stator magnets in there. So you see the B field, the alternating B fields. And then the E fields would be up and down at this point, and the force vector would be to the right. Now, what I'm proposing is you take the electric motor and you turn it on end. You now have a ring-shaped armature where all the force vectors are now pointing up. The B field now becomes radially outward from a magnetic pole, and the E field circulates in the ring. Now, one advantage of this system like this is it's a tuned system. If the magnetic pole is a half a wavelength and the E ring is, the circumference of the E ring is one wavelength, then it'll run at a fundamental frequency. And what that generates is a circular force field. And same principle, this is one cycle. Now the next cycle, the B field would be pointing in and the E field would reverse rotation, but the force pulses would just pulse up and down. They don't reverse due to the vector cross product. Now looking at it from the top, you have the center pole here, the radiating B field and the circular E field, and then the force vectors are pointing up. Now, rough specs on this guy, it's certainly better than a rocket. Top end is about 15,000 miles an hour, which is good enough to get you single stage to low Earth orbit. The problem is you're restricted to the planet's gravitational field. About 50,000 miles out, you're going to be out of gas. However, to go to the space station or out to geosync, one's about 200 miles out, the other is about 20,000 miles out, would be no problem. It would work quite well. However, if you wanted to go deep space or further out, you would have to use something that didn't rely on the specific gravity to push against to operate. So I would call it a warp drive. Been a Star Trek fan all my life, so that's where that name comes from. But the problem with space travel is the great distances involved, and to get anywhere in a reasonable length of time, you got to go very, very fast. And according to physics, your maximum speed is the speed of light, which is 186,000 miles per second. So in looking around for a starting point, the only machines that operate anywhere as close to this speed are atom smashers. So that's where I would start looking for incentive. So taking a look at a synchrotron or atom smasher, basically what it is you have a ring, and the operating principle is they put hydrogen in there, mainly I guess you'd call them protons. After they get down, breaking it down, they spin them around at a speed approaching that of light, which is like 0.8, 0.9 C. And then the beam is diverted out to a detector, and then they collide it with something, and the detector says, well, that's what happened. Now, this device is used in laboratories for subatomic particles and nuclear physics. What I would propose would be take two of them, two rings, you spin one clockwise and one counterclockwise, and instead of crashing them into a detector, you run them into a rocket nozzle. And you'd have to use two because if you just had one ring, you'd have a pinwheel and you just go around in circles real fast. That wouldn't get you any place. The problem is you would have to tune the rocket nozzles to space in order to get the maximum thrust. That I see as being the biggest part. Now, looking at the top view, you have two counter rotating rings, and then you have two output nozzles, one on either side. And that would also give you steerage. Like I said, the main point is getting a good balance, even with rocket engines. The bell on the rocket engine has to tune the thrust to resonate or to be compatible with space. So if you could tune those properly, you could probably pick up half your velocity. Okay, if you're going 0.8, 0.9 C as far as your jet velocity, a well-tuned system, you should be able to pick up about half of that, about say 0.5 C, which is a pretty good, remarkable increase over 30,000 miles per hour for rockets. Big problem is you're limited to the size of your fuel tank because you lose some mass in the system, same as with a rocket. However, your speed is going to be way up there. So a tank of gas will get you a lot further than with a rocket. And the other one is you don't have to ride the powder keg because your gas tank is water, not explosives. So safety wise, it's a much better deal. Whoops, we screwed up. Here, I wanted to back up. Let's try that again. There we go. On the specs on this guy, it's a synchrotron-based design, which could be used for interplanetary travel. It has a much greater speed, like 10x, if not more, than what a rocket is capable of. And that pretty much concludes my pitch. If you have any questions, see, how do I cancel this thing now?
Awesome, Mike. Well, thank you very much. Let me do this.
How do I pull the screen or the chart?
Yep. There we go. I stopped sharing.
Oh, you did. Okay. That's
yeah. And so what I'm going to do now is I want to put this in gallery mode. Everybody put your hands together. Big thank you for Mike. That was amazing presentation. Incredibly in depth and amazing math too, Mike. So thank you for.
I'm not a math guy, but I can follow the rules. So if it says differentiate, I differentiate, and then I just type it into the computer. When I ran this program on MATLAB, which is what made all the pretty pictures, it choked more than once.
Yeah, I can imagine. Those were pretty intense equations.
Yeah.
Well, let's do Q&A if you're up for it. We'll do a Q&A session. We're running ahead of time, but